Right, today's lesson on environmental chemistry is topic 3, which is how do you spell relief? So we will be looking at acids and bases today. All right, so acids and bases. So an acid, this is a chemical that produces an acidic substance, and it will have a pH value of less than 7. So anything acidic is having a pH value of less than 7. So some examples here: phosphoric acid. It's a key component in the manufacture of fertilizers, detergents, and pharmaceuticals. Another example, the flavoring agent in carbonated beverages, cheeses, jams, and jellies. So any food with a tangy flavor. Sulfuric acid is another ingredient or another example, of an acid. It is the ingredient in the batteries of vehicles. It's also used in the manufacturing of paints and dyes, refining of oils and gases, and the production of synthetic textiles. So that was sulfuric acid. All right, and then when we talk about a base, this is a chemical that produces a basic substance having a pH value of more than 7. All right, and when you do the brain pop activity, you will notice if it is basic, you will usually see like an OH negative. That's the hydroxide ion. So having a pH value of more than 7. Some examples of basic substances: sodium hydroxide. So again, here it has hydroxide, which is the OH minus. So you know that it's going to be basic. It's a component of household and industrial cleaners, in bleaching agents for the production of paper, fixatives in textile dyeing, solvents in making electronic circuit boards, a reagent in film processing. Aluminum hydroxide is another example. It's an ingredient in antacid tablets. So again, notice there's an hydroxide there. Okay, observable properties of acids and bases. So I do have an activity we'll be doing which will show some more properties of acids and bases, but for now, some properties are: acids taste sour, so for example, like lemons, and litmus paper. This is an indicator paper. Litmus paper will turn red when in contact with an acid, so that's shown here. This litmus paper is turning red when dipped into an acidic solution. Bases, they taste bitter, they feel slippery like soap. Soap is an example of a base. And then the litmus paper will turn blue when it contacts a base. So here we have litmus paper here, and this litmus paper is turning blue when it's dipped in an alkaline solution. And anytime you see the word alkaline, it means basic. All right, so an indicator, this is a chemical that changes color to indicate whether a substance is an acid or a base. And then litmus, like we saw the litmus paper, it's a mixture of plant compounds that is used as a chemical indicator. All right, so I do have a video here. This video is showing how you can make your own litmus paper using purple cabbage. All right, so pH, a powerful scale. So the pH scale, it's a way of comparing the relative acidity or alkalinity of a substance. So pH of 7 is neutral. It's not considered acidic. It's not acidic or basic. Once you see the pH below 7, it's acidic. pH above 7 is basic. So universal indicator or pH paper will change to a color that's characteristic of a specific pH. So instead of using litmus paper, there are other universal indicators that can be used. There's digital as well. So basically, if you're using a universal indicator, you would then match the color against a chart that will show the range of colors for the known pH values. All right, the other thing to remember is when we're looking at the power, like the pH, it means the power of hydrogen. So it refers to the formation of hydrogen atoms that have lost an electron. And each pH unit on the pH scale, it stands for a 10-fold increase in acidity or alkalinity. So basically, if you see a pH of 5.3, it's going to be 10 times more acidic than a pH of 6.3. If you were comparing 4.7 and 6.7, then 4.7 would be 100 times more acidic than a pH of 6.7. All right, so keep that in mind for pH. And again, it's the power of hydrogen. All right, so here we can see a couple ways to check the pH of a solution. This is the universal indicator paper. So you have this paper, you can dip it into the solution, and then you would match it to the color seen on this chart. And then you would have the numbers matched with those colors, the numbers representing the pH. And then there's also an indicator, universal indicator solution. And again, there's a chart on the bottle with the colors and the pH. And here is a digital method of measuring pH as well. All right, so just looking at this pH scale, so here we have 7 representing neutral. Anything less than 7 is acidic. So we can see things like really acidic or highly acidic, very acidic, like gastric acid in our stomachs. A battery acid would be around here. We have lemon juice at about 2, apple juice at about 3, and so on. Milk here is on the acidic side. Keep in mind that is pure water or distilled water. That is a pH of 7. And then as we go greater than 7, these are all basics. At the very end would be the very basic. So at 14 will be very basic. And keep in mind alkali. Anytime you hear the word alkali, it means basic. All right, so soaps, cleaning solutions, bleach, those are all considered basic. All right, let's watch a quick video here on the strengths and weaknesses of acids and bases. All right, so just to show here that if you do have a reaction between an acid and a base, it is a neutralization reaction, and then the products of a neutralization reaction will always be a salt and water. All right, so just looking here, we're just looking at some more properties of acids and bases. So formation of an acid or a base. So acids are formed from the reaction of nonmetal oxides with water, and then bases are formed by reacting alkali metals and metal oxides with water. So again, alkali. Taste. Acids taste sour, bases taste bitter. But again, for safety reasons, you shouldn't be tasting chemicals. The feel, again, you shouldn't be touching them either, but in general, acids are sticky. They can cause the skin to burn. Bases feel slippery, like soaps. They can also cause skin to burn. We looked at litmus paper reactions. So in an acid, the blue litmus paper will turn red. In a base, the red litmus paper will turn blue. pH levels of an acid are between 0 and 7. For a base, it's between 7 and 14. All right, so some reactions. An acid can react with a base to form salt and water. That's a neutralization reaction. It also can react with metals to produce hydrogen gas. They can also react with carbonates to form carbon dioxide, water, and salt. Bases, they can react with acids to form a salt and water. That's again neutralization. Some examples of acids are shown here, like the car battery acid. It's got a pH of about 0.3. It contains sulfuric acid. Stomach acid, which contains hydrochloric acid, can be about 1.0. And then there's others shown here as well, like tomato is about 4.5. Just keep in mind that they can vary, however, depending on concentration. And then on the right-hand side here, we have bases. So the human saliva has a range. It can be about 6 to 8. Blood plasma is about 7.4. Then we get more basic. Seawater is about 7.9. And so on. Here we have at 14, caustic soda. That's actually like drain cleaner. That's at a pH of 14. All right, so the activity here is organizing those substances on this pH scale. And then the second part, we just have like deciding whether these are acids, bases, or both, and then just completing some of these statements here. All right, so the next part of topic 3 is on acid precipitation. So oxides of carbon, nitrogen, and sulfur that are produced by burning organic materials react with the moisture in the air and form acids. So if we look here, this is sulfur dioxide reacting with water or moisture in the air to produce sulfurous acid. Here we have sulfur trioxide reacting with water. We're producing sulfuric acid. We have here nitrogen dioxide forming nitrous acid and nitric acid. And then we have carbon dioxide reacting with the water or moisture in the air to form carbonic acid. All right, so these are different types of acids that are forming from the burning of those organic materials. One thing to note is acid precipitation that is coming from one country can cause, so basically if the emissions are coming from one country, it can cause acid precipitation in another country. More than 50% of the acid precipitation that affects Eastern Canada is due to oxides that are originating in the US. Okay, so keep in mind that emissions can travel and cause acid precipitation somewhere else. All right, so acid precipitation, this is any rain or snow containing acid compounds from the air. So basically these acid compounds are washed out of the air by the rain and snow, and then they're deposited a long way from the sources of the oxides. So it looks, acid precipitation, it looks, feels, and tastes normal, but it does cause a lot of damage each year. It'll damage, for example, aquatic ecosystems of lakes and streams. It reduces productivity of crops. It harms vegetation. It can also accelerate the decay of buildings and structures and so on. Acid that gets added to the soil dissolves mineral nutrients and allows them to be leached or washed away. That'll result in soil that is nutrient poor and then therefore poor growing conditions for plants. In this diagram here on the right, we can see maple leaves showing damage due to acid precipitation. So using chemistry to control acid effects. So in Western Canada, rock debris left behind from melting glaciers, they contain a substantial amount of alkaline minerals such as calcium carbonate or calcite. And this calcium carbonate that's lying at the bottom of the lakes, it neutralizes the acids that are entering these lakes. And one major source of calcium carbonate is limestone. So there's a process called liming, which basically is adding calcium carbonate to the environment. And we see this acid-base neutralization occur, which is the combining of an acid and a base to produce salt and water. But the question is why can't we neutralize the effects of acid precipitation in all the acidified lakes if it's so easy? All right, so in these two images, here in this image, we can see liming occurring here. So releasing the powdered calcium carbonate from aircraft. In this image, many monuments and statues, some that are thousands of years old, they're made of marble and limestone. And these substances, they contain calcium carbonate, which is easily decomposed by sulfuric acid. So we can see the reaction here. Calcium sulfate dissolves in water more readily than calcium carbonate. Thus, the monuments and statues corrode as the calcium sulfate is washed away. Just some information here. Normal rainwater has a pH as low as about 5.6 because of carbonic acid, which is formed from carbon dioxide gas dissolved in water. sulfur oxides and nitrogen oxides from industries and transportation results in rain that is even more acidic. Central Europe, Japan, and Eastern North America are severely affected by acid precipitation. Rainwater can have an acidity approaching that of vinegar, pH of 3, which is 1,000 times more acidic than normal rainwater. Even more acidic, extreme acidic conditions. In 1974, there was a storm that dropped rainwater with a pH of 2.4 over Scotland. And Los Angeles has been measured to have a pH as low as 1.7. That's 10,000 times more acidic than normal. So using chemistry to control harmful emissions, so alkaline substances, they react with acids in a neutralizing reaction. So we talked a little bit about liming. It has limited success. Rivers and streams, they're constantly feed acidified water into the lakes. So then the lakes would have to be limed continuously to keep up with the new influx of acid. So it's impractical. It's also expensive. So since it's impractical and expensive to neutralize all of the acid precipitation humans are causing, we have to reduce or eliminate the oxides. So engineers, chemical engineers, they design and build devices that can remove oxides before they get into the air. So there's one device called catalytic converters. These are devices in vehicles that encourage complete oxidation during combustion. So a converter, it aids the formation of carbon dioxide and water from hydrocarbons, reducing the amount of carbon monoxide and nitrogen oxides produced. So basically the purpose of the converter is to encourage complete oxidation. That's that reaction where oxygen combines with other elements to form new substances. All right, so here is a catalytic converter. They're quite efficient, but they work best when the catalysts are warmed up. It takes about 90 seconds after a car starts for the catalyst to be activated, but unfortunately, it's during that brief warm-up that the car produces about 70% of all the pollutants that it releases during its driving cycle. We also have scrubbers. So oxide emissions from industrial factories and power plants that burn coal, they're a major source of oxides. So installation of scrubbers, it reduces oxide emissions. So these scrubbers, they are anti-pollution systems. They remove the sulfur dioxide and contaminating gases that are resulting from the burning of fossil fuels. All right, they use this sorbent material which reduces oxide emissions. So it's basically a substance that absorbs oxides. COBRA, which stands for copper oxide bed regenerable application. So this system, it uses a sorbent of small beads of aluminum oxide, which is impregnated with copper. And this has shown in tests that it removes all nitrogen oxides and about 95% of the sulfur dioxide from emissions. So these copper oxide sorbents, they are more expensive to produce than sorbents in traditional scrubbers, but it is reusable, so therefore costs are recovered over time. Right, so they look like little beads, and they remove sulfur dioxide and nitrogen oxides. Those are the pollutants responsible for acid precipitation. So they remove the sulfur dioxide and nitrogen oxides from gases that are given off during coal combustion. All right, a couple videos here to watch, so I'm just going to pause here.